What if a tiny piece of power electronics could cut charging stress, slash cable losses, and actually help your battery live longer? It's not magic, it's smart conversion. You're digging into a bold question. Can boost converters, the DC-DC devices that step voltages up or down, change the story of fast charging and battery aging? Today, I'll show you how they work, run the real numbers so you can see the savings, explain where they help the battery and where they don't, and point to experiments and studies that matter. If you care about faster stops, fewer battery headaches, and less wasted energy, this video is for you. Hello everyone, I'm Shayan, an engineer specialized in electric vehicle development. What is a boost converter and why engineers care? A boost converter is a DC-DC power stage that raises voltage from one level to a higher level, while controlling current precisely. In EVs and chargers, it can sit between the charger and the pack, or be built into the station or vehicle as part of the two-stage architecture. The converter does three useful things for charging. It lets you deliver the same power at a high voltage and lower current, which cuts resistive losses in cables and contacts. It allows fine, active control of voltage or current ramps to shape the battery's stress profile during charging. And when bidirectional, it enables V2G or V2H functions and active balancing schemes that can move energy between modules for healthier cells. These are powerful sounding benefits, but the key is how big the numbers actually are in the real life. Numbers that make this interesting. A simple math example. Let's make this concrete so you can see the leverage boost converters offer. Imagine a 150 kilowatt DC fast charge into a 400 volt pack architecture. Current equals to the power divided by voltage. 150,000 divided by 400 volts gives you 375 amps. If the cable round trip has 0.01 ohm resistance, resistive losses is around 1406 watt loss as heat in the cable. Now use a boost converter to step the bus to 800 volt before the cable. Current becomes 150,000 watts divided by 800 volt, which is 187 amps, which gives you 351 watts of loss. That's roughly a fourfold reduction in cable loss. A real measurable saving that reduces wasted energy and heat in the cable and connector. High voltage distribution is exactly why many OEMs are moving toward 800 volt systems for ultra fast charging. Efficiency and converter losses, not free but close. Boost converters aren't lossless. Modern high quality DC-DC converters can hit very high efficiencies. Prototypes and research show peak efficiencies in the mid high 90s, like 97% in some lab designs. That means the converter's own loss might be only a few percent of the power, often far less than the resistive savings you achieve by raising voltage and cutting current. So the net system efficiency can improve even after adding the converter. Experimental prototypes have demonstrated efficiency improvements of a few percent versus less optimal topologies. How converters can reduce battery stress during fast charging? Battery degradation from frequent fast charging is complex. It is driven by peak currents, cell polarizations, lithium plating risk at low temperatures, and thermal cycling. Boost converters enable more nuanced control of the voltage or current trace the battery sees. By shaping the current ramp and avoiding sudden high current spikes, converters reduce instantaneous stress. By enabling higher distribution voltage, they cut current in cables and contactors so less heat reaches the pack area. When paired with active cell or module balancing DC-DC stages, they can equalize module voltages and prevent some modules from hitting high state of charge earlier than the others, which lowers the need for aggressive top-end tapering. Research on active DC-DC balancing shows architectures that move charge between modules in real time can reduce energy losses and keep cell voltages aligned. That improves usable capacity and can slow net degradation. That's not hypothetical. Papers and prototypes in 2024-2025 demonstrate active balancing topologies that help the charging flexibility and reduce wasted energy. Bidirectional converters, V2G, and life cycle trade-offs. If the converters are bidirectional, they become doors to V2G and vehicle-to-home services, which shift when and how the pack is cycled. Some recent studies suggest controlled bidirectional usage. With smart limits, doesn't necessarily accelerate degradation and can even help by smoothing cycles when combined with intelligent control. But the details matter here. How deep the discharges are, the timing, and the thermal environment all change the outcome. So converters that enable V2G must be paired with a careful battery management policies. So if boost converters have these advantages, why aren't they already everywhere? A few practical blockers: cost and complexity. High power, high efficiency DC-DC stages, especially bidirectional ones, add hardware costs, cooling, and control logic. Prototypes exist, but mass deployment needs cheaper, ruggedized designs. Thermal management: putting a high power converter near the pack or in charger needs good cooling. That adds weight and packaging challenges. Integration and standards: many chargers and vehicles assume direct DC transfer. Adding converter layers need coordination of communication layers and standards across vehicle and network. What fast charging does to the battery today? Frequent high-power DC charging pushes cell into high current and thermal swings. Fleet and telematics studies show more frequent DC fast charging correlates with faster capacity losses. Though the exact rate varies by chemistry, thermal design, and usage patterns, one recent fleet data update reinforced that frequent fast charging can accelerate degradation. The devil is in the frequency and conditions. That's why anything that meaningfully reduces current and heat in the pack is worth looking at. Can converters be fixed or just part of it? Boost converters don't erase the physics of battery chemistry. They're a system tool. They reduce currents and resistive losses and enable smarter charge profiles and balancing. But to truly limit degradation, you need an integrated approach. Thermal systems, battery chemistry optimized for fast charge, cell designs with low lithium plating risk, and smart charging algorithms working in the converters. Recent reviews of fast charging advancements stress that power electronics are a key part of the solution but not the entire answer. Where converters make the biggest difference? High power public charging hubs. By boosting station voltage near the charger, you can reduce side cable losses and allow stations to deliver more effective kilowatts without dramatically upsizing infrastructure. That's already a trend. Higher system voltages are used to reduce grid side currents. Vehicles with modular packs. Active DC-DC balancing can improve pack uniformity and allow more aggressive but safer charging profiles, because modules won't cross-stress each other. Prototype papers show this can help reducing the losses and providing finer control. Fleet propagations, fleet operations, and depot charging. A converter-enabled depot can smooth charging and manage battery temperature and state of charge to minimize cell stress, which can in return reduce overall life cycle costs even if hardware costs are higher upfront. Real depot and fleet studies highlight the economics of reduced downtime and slower degradation. So, what the early real-world evidence says. Industry and academic work between 2022 to 2025 show promising prototypes. High-efficiency DC-DC stage integrated systems that reduce total energy loss a few percent. And V2G pilots that, when controlled, don't necessarily shorten battery life. The numbers add up. Cutting a few percent of losses and reducing peak cell currents by 2 to 3 times can translate to meaningful lifetime improvement. But long-term field data over 8 to 10 years is still emerging. That's the current reality. Lab and pilot evidence is positive, but watt-scale multi-year fleet data is the final arbiter. Boost converters can be a game changer for a system. They reduce cable losses dramatically at higher voltages, enable fine charging shapes, and support active balancing that helps cell health. In practice, the most attractive use is where they lower current dramatically, because resistive losses scale with current square. Modern power electronics reach efficiencies that make the converter overhead smaller than the savings for many use cases. But they are not a silver bullet. You will need cell chemistries and pack cooling that tolerate faster fills, and you must accept higher system costs and added complexities. Wide adoption will come, and when the converters become cheaper, standards converge, and long-term fleet data confirms life cycle benefits. Industry moves in that direction. Manufacturers are exploring integrated power modules and higher voltage packs to capture exactly these wins. Quick takeaway: what drivers and fleet managers should know. Boost converters can reduce cable losses by multiples when they let charging happen at higher voltage. That's pure physics and immediate benefit. High quality converters can be 95 to 98% efficient, so converter losses are often smaller than saved resistive losses. Look for wide band gaps. They drive those efficiencies. For battery life, converters help when paired with smart charge protocols and thermal control. They're part of the toolkit, not the whole fix. Controlled moderate charging and good thermal management still matters most.